Okay, let's get started with lecture 11 in statics. So we're pre-recording this lecture because our college is going on a retreat this week. And I'm actually recording this somewhat early, about a week in advance. So some of these announcements, I guess I'm predicting what the announcements will be. So first off, the attendance grades, they should be up to date. In terms of the homework structure, the homework 2.6 should be graded, or should be graded, or to be graded. I say to be graded because it might still be working on it. Hopefully the TAs are able to keep up with that. Homework 2.7 will be submitted at the time this lecture is posted, and I'm going to assign homework 3.1 today. But it's not going to be due until after the first exam because this material isn't going to be on the first exam. So in terms of the lecture next week, we'll have exam review on Monday, and I'll have talked about that before this recording, so you'll know what to expect there. The exam will follow on Wednesday, and then on Friday we'll begin our exam 2 material, which this is sort of starting the coverage of exam 2 material in the discussion of cross products, but we'll formally start it then. Okay, so before I begin, I'll go ahead and mention that today is going to be somewhat of a math heavy lecture. We're going to be doing some derivations. There's going to be some formulas and equations. I lost my pen here, but I'll find that in a second. In the meantime, what we're going to be doing today is discussing basically how to multiply vectors. And so there's going to be some derivations and geometry and so on and so forth. So I just want to prepare you for that in advance. And I'm going to sort of distill that into really only what you need to know as students of statics. But I do want to give you the context at the same time of what we're doing and why we're doing it. Okay, so let's begin with just what a cross product is, and why we use it, why we need it, and so on and so forth. And I'll very lightly touch on why we need it because that'll be the focus of the next few lectures. But let's first off talk about what a cross product is. So by now, I think that everybody in the class should be very, very comfortable with adding vectors together, or taking vector A and vector B and adding it by components. You should also be able to take vectors and multiply them by scalars. So if you have a vector P, you should be able to figure out what 2P is and so on and so forth. So adding vectors together, multiplying them by scalars. If you ever took a course in linear algebra, they would call that a linear combination. Everybody in the class should be very, very comfortable with doing that stuff. But we now need to discuss how to multiply vectors. And it's very, very important in assessing rigid body systems because the cross product of two vectors leads into the formal definition of a moment, which is what rigid body evaluations are all about. Now, there's actually two ways of doing it, and it's all about what you want your result to be at the end of the day. If you want your result at the end of the day to be, let's say, a scalar. So you want vector A times vector B to be a number. Maybe vector A times vector B is 6. Okay, that's a scalar product. And the way that we represent that, let me see if I can find my little thing. Here it is. And so the way that we represent that is we represent that with a notation. So let's say I have vector A and I have vector B. Okay, if I want the answer to be a scalar, so like A multiplied by B gives you 5, I represent that with the following notation. I say A dot B. And so we commonly refer to that as a dot product. So whenever you dot two vectors together, you get a number. But if you want a vector at the end of the day, if you want A multiplied by B to give you another vector, then we represent that with, sort of the X multiplication symbol. And so we call that a cross product. In fact, probably from here on out, I won't refer to them as scalar products and vector products. I'll call them dot products and cross products. And so what we're going to be focusing on today is the cross product, which admittedly is the more difficult one, but it's the one that's more immediately useful to what we're doing in statics. Now, in order to generate a formula for the cross product, we really need to define what the cross product, or what we want the cross product to be at the end of the day. So we understand that if we have vector A and vector B and we cross them, we do a cross product, we want a vector. We want A cross B to yield another vector. But what's going on with that vector? We need to have some definable goals. Well, if you recall, and we've been harping on this, throughout the entirety of the semester, that a vector has two fundamental properties. Remember, a vector is a mathematical object that contains two pieces of information, a magnitude and a direction. Okay. Now, if we have two vectors in space, so we have vector A and vector B, and they could be pointing in any which different direction, okay, we need to define the cross product in such a way that rigorously defines what's going on with the magnitude and direction of that result. So in terms of direction, what we're going to do is we're going to say that whatever A is and whatever B is, when you stick those two things together, you can form a plane between those spaces. So here's vector A, here's vector B, and we can pretty easily define this parallelogram, this plane that's defined by these two vectors. And so what we're going to do is we're going to say that the cross product points perpendicular to that plane. Although I won't use the term perpendicular, I'll use the term normal to the plane, because perpendicular just defines two lines forming a 90-degree angle. Whereas normal says, okay, if this is my plane, right here, and this is my vector, a vector normal to the plane forms a right angle at every direction. So it's completely perpendicular to all directions along that plane. So we call that normal. So like this would be a vector. Let me move into the camera. This would be a vector normal to that plane. So there's the direction. So A cross B needs to be normal to the parallelogram, the plane formed by A and B. As for the magnitude, what we'll do is we'll say that the magnitude basically needs to equal the area formed by the region bounded by A and B. So for example, if let's say this was my parallelogram, and this is vector A and this is vector B. And so if vector A is, let's say, 3 units long and vector B is 5 units long, the idea is that the cross product would be such a vector that, if I did A cross B, that the magnitude of A cross B would be 15 if this was 3 and this was 5. And then, it would be normal to, the direction would be normal to that plane. So that's basically what we're defining the cross product to be. And from a mathematical perspective, we're doing that because that's really the only way that we could define it that would work for any vectors. Like, it doesn't matter what vector A is and what vector B is. We can define this these results such that it'll work for any vector that comes into it. Now, one of the things that's worth mentioning is that unlike with adding vectors, the order matters. Okay, so if you take vector A plus B, it's the same thing as taking vector B plus A. The addition of vectors doesn't matter in terms of the order. We call that commutativity. But for multiplication, it does matter. In other words, A cross B is not the same thing as B cross A. Okay, so if you go back to the idea of the result being normal to the plane, the way that we define that mathematically, or the way that we remember that how that works mathematically, is we use a moniker called the right-hand rule. And so the way that the right-hand rule works is, let's say this is my plane, and let's say this is vector A and this is vector B. I'll try and move into the camera here. What we do is, the way the right-hand rule works is we take our fingers and we point them towards the first vector, and then we curl them towards the second vector. So let's say this is vector A and this is vector B. So we point them towards A and curl them towards B. And whichever way our thumb is pointing, that will be the direction of the cross product. So A crossed with B goes like this. Whereas if it's the other way, if it's B crossed with A, then the direction's opposite. So A crossed with B, B crossed with A. So whenever you switch the order of a cross product, you change the sign. So A cross B is the same values as B cross A, but the signs are flipped. So again, the order of operations matters when it comes to cross products. A cross B does not equal B cross A. A cross B equals the negative of B cross A. So that's really important to remember, that the order matters. Now, hopefully I think the idea makes sense in terms of what we're doing and what we're trying to achieve in regards to the cross product. But that doesn't really help us in terms of defining a formula, if you will. We want a formula for the cross product. And the easiest way to define that formula is to look at our base vectors, our IJK, our essential unit vectors, because they work out really well in terms of understanding the math. First off, remember, each of the vectors has a magnitude of 1. So let's start off with a very basic example. Let's do I cross j. Let's see if we can figure out what I cross j is. Okay, let's go back to our definitions. Okay, what do we want the magnitude of I cross j to be? Well, we want the magnitude to be equal to the area formed by the parallelogram between I and j. Well, let's look at this graph here. This is the parallelogram formed by I and j. Okay, and the question is, what is the area of that little square? And keep in mind, it's a square because these are all 90 degrees. And what is the area of that square? It's 1. Okay, so first off, there we go. Okay, so we know that the result needs to have a magnitude of 1. What about the direction? Well, this is where the right-hand rule comes into play. So imagine taking your hand, okay, facing your fingers toward the x-axis and curling them up towards the y-axis. And imagine doing that while you're watching this video. Facing your fingers towards the x-axis, curling them up towards the y. Your thumb should be pointed at you, at your person. So your thumb would be pointed out of the screen, and your thumb would be pointed, sort of in this direction if we're looking at it isometrically. So what do we have here? What do we know about the cross product of I cross j? Well, the cross product of I cross j needs to have a magnitude of 1, and it needs to point towards the z-axis. And the question is, what vector has a magnitude of 1 pointed towards the z-axis? Well, it's simple. It's k. Okay? So if you take I crossed with j, you get k. Okay? And you can see this for some of the other patterns as well. Okay, what happens if you do j crossed with k? Well, imagine, no matter what vectors we're talking about here, let's first off think about the magnitude. If you're crossing any of these, opposing vectors together, like j and k, or I and k, or j and I, or what have you, the magnitudes are always going to be 1. Okay, because those are always going to be those little squares that you're forming. So it's either going to be that square, or maybe even that square, something like that. So the magnitudes are always going to be 1. And as for the directions, you can follow your right hand rule pretty easily. So what about j cross k? J cross with k, your thumb should be pointing in the positive x direction. So j cross k is I. What about k cross I? Again, same idea. K cross I is j. All right. Now, similarly, what if you flip the direction? Okay, so what about this right here? Okay, so I cross j is k. What about j cross I? Well, again, it's the same magnitude, but if you follow your right-hand rule, your thumb's going to be pointing in the opposite direction. So it's going to be pointing along the negative z-axis. So it's a magnitude of 1, but you're flipping the directions. That's why you change the sign here. Anytime you flip the order, for instance, right here, you flip the sign. Okay, now, that's what happens when you're crossing these when you're doing these cross products involving opposing vectors. What if you cross a vector with itself? What if you do I cross I, or j cross j, or k cross k? Well, it should make sense that the answer to that is going to be 0, because if you look at I crossed with itself, there's no parallelogram. There's no region formed by a vector crossed with itself. So the cross product of a vector with itself is always 0. Okay. And that is also true of any vector, not just the unit vectors. If you take a cross a, you're going to get 0 for any vector a. So the reason why we're looking at this is because what we're going to try and do is compute the cross product of an arbitrary vector. Like cross products of I, j, and k are very simple, but cross products of an arbitrary vector takes a little bit of work. I'll go back to I'll go to that slide here in a bit. So let's go back to the goals of the cross product. Okay, so what do we know about the cross product? We know that a cross b points in a direction normal to the plane, and we know that A cross B has to equal the area formed by that. Now, how do we compute it? Well, the answer is, if we want to compute the cross product of an arbitrary vector, we use what we learned from IJK. Now, I'm going to draw this on the notebook here in a second, but there's a simple moniker that we use whenever we're trying to remember cross products. Is what we do is we draw IJK, and we draw sort of a circle around it that goes like that. That's very horrible in terms of the artwork, but the idea is retained. The idea is that we draw IJK, and if we're following the circle, then the answer is the positive result. So, like, for example, if I do K cross with I, I'm following that circular direction that's indicated here, that clockwise direction. So if I go clockwise along this circle, K cross I is J, and that's a positive answer. If I'm going in the opposite direction, K cross J, that's the opposite direction, so that would be negative I. So it's sort of a simple way of remembering what the cross products are, so you don't have to remember all of these formulas. This is just a little shorthand, and I'll use this here in a second. Okay, so in order to determine the cross product of some arbitrary vector, I need to use the cross products of I, J, and K. And when you do that, you get this. And I can already imagine it's like, whoa, there's a lot going on here. So what we're going to do is we're actually going to break away from this slide real quick, and I'm going to open my, my little OneNote here. And where is that? Right here. I'm going to open my OneNote here. Let me use this. And we're going to do this derivation together. I think that this is very valuable to do collaboratively. And once you understand how this works, it's not so bad. Okay, so I have vectors here. I have, vector P and vector Q. They're just arbitrary vectors. It doesn't really matter what they are. Like P could be, 3i plus 6j minus 4k. I'm just using these little px, py, and pz's to refer to the constants being multiplied. It doesn't matter what they are. And what I'm going to do is I'm going to do p cross q and see what you get. Now, the way I'm going to do that is the way that you would multiply numbers or polynomials, the way that you would do any multiplication. So what we're going to do is we're going to say px plus py, sorry, get ahead of myself, plus pz multiplied by qx plus qyj plus qzk. And so what we'll do is we'll, multiply these and see what you get. Okay? So how am I going to do this? I'm going to do it like you would, like when you first learned how to do multiplication. So we'll do pz qzk plus py qz. Actually, hold on. Let me rewrite this. Okay, so let me guide this a little better. So first thing we're going to do is we're going to do this times this. And so what I ought to do is actually write out the k cross k right here. So that's this term. Okay. So what am I doing here? I'm taking the constants times the constants, or the scalars times the scalars, so pz, qz, and then k cross k. I'm just following out the algebra. Plus, okay, now what we're going to do is we're going to do this times that. So what do we have? We have py, qz, we have j crossed with k. All right, and then we'll do this times this. So plus px qz I cross k. Okay, so see what I'm doing here? So see how I'm just, this term times this term, plus this term times this term, plus this term times this term, and I'm just going to keep doing that throughout the entirety of this process. So now let's do the second row. Okay, so, or the second term here. So we're going to do that times that, and then times that, and then times that. So let's see what we get here. So plus, what do we get? P, Z, take a mark through that, Q, Y, and we get j crossed with k, right? I got my little cheat sheet here to make sure I don't have any typos here. P, y, q, y, j crossed with j, and then p, x, q, y. And so and one of the other things that's really important is that I'm maintaining the order, right? It's P crossed with Q, so the P terms are always coming first, okay? Plus, and then now we're going to do the same thing with this, okay? So PZ, QX, K crossed with I, plus PY, QX, J crossed with I, and then PX, QX, whoop, QX, I crossed with I. Okay, so to be clear, that's the cross product, okay? That's the answer, but that's a lot. So can we simplify this? Yes, we can simplify this. And we can simplify this using the moniker that we know with the cross products of the unit vectors. Now I'm lazy here, so what I'm going to do is I'm actually going to copy this whole thing. Let's see if I can copy that. There we go. So I want to look at this, and I want to see if there's something that we can do to this to make our lives a little easier. Okay. The first thing that I want to do is recognize that whenever you have a vector crossed with itself, that you get the zero vector. So what that means is that these terms right here, this term and this term, I can cancel those out because those are going to be zero vectors. So they're technically zero vectors, or not just zero, because we're taking vectors and adding them to vectors, but all the terms are going to be zero, so it's the same idea. All right. Now what I'm going to do is I'm going to use this moniker here to see if I can simplify this result a bit. Okay, so let's start off with this first term right here. Let's start up with this. Okay, I cross K. What is I cross K? We'll follow the moniker. I cross K means we're going that way. So that's negative, right? So I cross K means we're going negative. So this is going to be negative J. Okay? See what I'm doing there? And again, if you don't follow the moniker, you can just go back to the slides here that we had found right here. Let me see. Oh, sorry. We can go here, and we found that. Sorry, I've got multiple monitors here. So we found that I crossed K was negative J. You can see that right here. So it's not like we're revealing anything that we can't just pull from our previous derivation. Okay, so let's go back to our notebook. All right. Let's see. Okay, so now we just keep on going. What is J crossed K? Well, J crossed K, again, we're going positive. That's plus I, right? I cross J down here, that's plus K. J cross K, that's plus I. J cross I, that's negative K. And this K cross I is going to be positive J. And you can notice there's kind of a pattern here, because think we've got a plus K and a minus K, a plus I and a minus I, a plus J and a minus J. There's a pattern there. And that's probably the most important thing to recognize, is that there is a pattern to this, and we're going to use the pattern to make our lives a little easier when actually doing cross products. So now what I'm going to do is start to collect. Well, first off, let's do this. Let's rewrite this a bit. So we have negative px qz times j plus py qz times I. Then we have, and so now what I'm doing is I'm basically just going to write this in one big old expression. So we have plus pxqy times k plus pz. Wait, I think I have a sign error here. Oh, I do, yes. I think I have a sign error there. Let's see, what do I have? Let me check something. Ah, that's the problem here. This one is an error. Let me go back to, let me see something. Do I have a sign error here? It looks like I should. Let me check here. PXQZ, that's negative J. PYQZ, that's positive I. PXQY, that's K. My apologies here. PZQY. This one here is supposed to be negative I. Sure why. I think I must have had a typo there somewhere. But yeah, that one's supposed to be negative I. This one's supposed to be negative. I'm going to check this here in a second. I'll check this and see why that's supposed to be. That's supposed to be negative I. Okay. All right. So next one is negative PYQX times K and plus, here, let me see if I can move this over a bit. Plus PZQX times J. Okay, so these are our terms that we've now since simplified, and now all I'm going to do is collect everything that has an I in it, collect everything that has a J in it, collect everything that has a K in it. And so what I'm left with is PYQZ minus PZQY times I plus, and see, again, notice there's a pattern here. PZQX minus PXQZ times J. So if you're not following this step, what I'm doing, and I'll take a second here, is I'm basically looking at all the terms that have I, J's, and K's. So for instance, here are the terms that have I's. And so I'm just collecting those all together. These are the terms that have J's, J's, and J's. So I'm collecting all the terms that are together. And then finally, PXQY minus PYQXK. Again, just collecting all the like terms. And this right here, this is about the most distilled formula we can get. This is the cross product. Okay? Now, before we leave, I'm going to see if I can isolate what had happened with these signs, because it's going to bug me if I don't follow this. Because I think what's supposed to happen is maybe what I had done. That was the problem. I know what the problem is. This was in the wrong order. That was supposed to be K cross J. That was the problem. Whoops. So this one right here was supposed to be K cross J, and that crossed out to be negative I. Whoops. All right. So what I'm doing here is, just to follow us along, I know it's a lot of algebra, but it's kind of repetitive. Is I started off, I had the vectors, multiplied it out, then I used my unit vector observations to see if I could simplify it, and then factored it. And that's the cross product. The problem is that even though there's a pattern, and I think you can kind of see that there's a pattern here. So for instance, if you look at the I terms, look at what's in front of the I, right? if you look at what's in front of the I, there are no x terms, so there's no px or qx, and it's almost like a determinant, right? If you remember, how do you do a determinant? Let's see if you remember how to do a 2 by 2 determinant. What is it? AD minus BC. If you remember that, it kind of looks like a determinant. What's being multiplied by these components here, like for the J vector. Or for the J vector, PZQX minus PXQZ. It's almost like if it was, you know, I don't know, maybe PX or PZ, you know, maybe if it was like a determinant. Instead of figuring this out, I'm going to show you that's actually what we're going to do here in a bit. But ultimately what we're going to do is we're going to use determinants to make this a lot simpler. To be clear, I'm not going to make you do any of this derivation on any exams or anything. I'm going to show you the straightforward approach here in a bit, but I just want you to understand where this formula comes from. The big thing to keep in mind, though, is that we are not going to make you do this by hand. But again, this determinant approach is going to simplify things. Okay, let's go back to the presentation. All right, so so what you see here is just honestly a lot neater what I just did on the notepad, but I think it's worth it to take the time to do that. Is basically following through that peak plus Q process. So, okay, is there a way to simplify this? Yes, the answer is to use the determinant. So let me back up and see if anybody has ever if you haven't used the determinant or haven't seen the determinant before. So in matrix algebra, and we've done matrices in here already, I know, because at this point, I know I'm pre-recording this lecture, but at this point we should have done 2 by 2 systems and 3 by 3 systems, so I know you all know what a matrix is. A determinant is a numerical value. It's a scalar that serves as a very important characteristic of a matrix. And while this isn't a matrix algebra class, this isn't linear algebra. If you take a course in linear algebra, you'll see that determinants are very, very important. They tell you whether or not matrices are singular, and there's a big to-do in linear algebra about determinants. But for our purposes, what you can see is that the determinant is a very, very valuable tool for us to determine cross products, because if you look at the formula for doing a determinant, so for example, if you remember, as I mentioned here, I'm getting ahead of myself already because I was saying the answer as I was writing the determinant. If you have a 2 by 2 determinant, the answer to that is AD minus BC, and that's very akin to what we're seeing here. Again, if you had PY, PZ, QY, QZ, and you just determine that, you would get P minus PZ, QY. That's the same thing you have here. So there are some parallels there. So we can use determinants to make our lives a little easier when memorizing this formula. Now, the determinant for a 2 by 2 matrix is really easy. It's just a formula. It's just AD minus BC. But for a 3 by 3 matrix, and for matrices that get larger, algorithmic approach to it. Now, the way that we're going to determine a cross product instead of using this bulky formula is to use this. Okay, so basically what we're going to do is we're going to set up a determinant. Okay, and on the top row we're going to put ijk. On the middle row we're going to put the coefficients for the first vector, and on the bottom row we're going to put the scalar coefficients for the second vector. And if we evaluate this determinant, it is the same thing as plugging and chugging into this formula. And again, the value of the determinant is that you don't have to memorize the formula. All you have to do is memorize a pattern, and it's a lot easier to memorize the pattern. I'm going to show you 2 different ways to do it, and I show you these because they are I guess checks of one another, and some of them have advantages over the others. The first is called the rule of Saris. If you've and to be clear, if you've taken a course maybe in Calculus 3, if you've had Calc 3 yet, you've probably seen these already. So this should be reinforcing what you've already seen. But if not, just know that these two methods just can serve as checks of one another. The rule of Saris, I think, is easier the first time that you start doing it. I actually prefer cofactor expansion for a good reason, and you'll see why in a bit. But I'll show you how each of these work with some numbers here in a bit. But basically the way the rule of Saris works is you set up your determinant, and what you do is you repeat the first two columns on the right, and basically you take all of your products this way minus all of your products this way, and that will give you the determinant. Cofactor expansion is a little fancier. Basically what you end up doing is you sort of expand along the top row and you flip your signs. It seems like it's a little bit more to memorize, but the result at the end is much cleaner, and that'll become clear as we do this example. I think it's time we start doing an example. So I have here two vectors, 2i plus j plus k and negative 4i plus 3j plus k, and we're going to determine the cross product two different ways to see that you get the same answer. I'm also going to show you how to do it on the Casio real quick because it's not that difficult. Okay, so where's my mouse pointer? There we go. Let's go to cross product. All right, so a couple things. We're going to do the cross product here, and so ultimately what we're going to do is the cross product of, so the way that you set this up is you write your unit vectors on the top row. On the middle row, you write the coefficients for the first vector. So that's going to be 2, 1, and 1. Now, because the I and the J, or the J and the K, they don't have coefficients, but they do because everything's multiplied by 1. And as for B, it's negative 4, 3, and 1. Okay, and that's what we want to find the cross product of. Okay, so we're going to do this two different ways. The first way that we're going to do it is called the rule of Saris. So let me show you how the rule of Saris works. Okay, so to do A cross B, what you do the rule of Saris, what you do is you repeat the first two columns over here on the right. So you'd say I, 2, negative 4, J, 1, and 3. You just rewrite them, okay? And what you then do is you say, okay, I'm going to take all of my products first this way. So you do this sort of diagonal, I don't know, like checkerboard type thing. You do those products, okay? So let's do those. Let's see what you get. All right, so for the first one, what do you get? You get I times 1 times 1, you get I. For the second one, J times 1 times negative 4, negative 4J. For the third one, K times 2 times 3, 6K. Pretty simple. Then what you do is you take the products going the other way. So we're going to do this, 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 okay? So let's do that. So what do we have? We'll start at the right and work our way over. So J times 2 times minus 1, or sorry, J times 2 times 1 is 2J. I times 1 times 3 is 3I. And then K times 1 times minus 4 is minus 4K. And then in order to compute the cross product, we take the difference of these two. So we take the products this way minus the products this way. So now what we have to do is start grouping like terms. So for I, what do we have? We have 1 minus 3, okay? For J, what do we have? We have negative 4 minus 2, okay? And then for K, For k, what we get is 6 minus -4. So you got to be really careful about the signs here. Okay, that's one of the things with the rule of Saris. This is really easy to do it, but you just got to be careful on the arithmetic. So minus 2i minus 6j plus 10k. And so that's the cross product right there. That is a way of doing the cross product. Okay. Now, the other way of doing the cross product, I think by hand, that is easiest, is cofactor expansion. Okay, so what about cofactor expansion? So let's rewrite it. Okay, so the way cofactor expansion works, it's just another pattern, and you'll see why I kind of like it here in a bit. But the way cofactor expansion works is you usually expand along one of the rows or one of the columns. And so the row I'm going to expand upon is the top row, because I want a pile of junk times the first term plus a pile of junk times the second term. So I want the result to be ijk. And so the way that this will work is I'll start off, I say expand along the first row. What that means is it's going to be I times a smaller determinant, and then j times a smaller determinant, and then k times a smaller determinant. And then what you do before you fill in those determinants is you alternate your signs. Like this is positive, this is minus, this is positive. And so usually what I'll do is I just won't even write that first one. So I times a determinant minus j times a determinant plus k times a determinant. And then what are those determinants? Well, the way that you do this is, okay, so let's take the first one, the I term. So what I do is I cross out the row and the column associated with that I term. And what I'm left with is 1, 1, 3. I use to determine that coefficient. Okay, what about the j term? Okay, so the j term, I cross out the row and the column associated with j, and I'm left with 2 minus 4, 1, 1. Okay, and for the k term, again, same idea. Cross out the row and the column associated with that k term, and I'm left with 2, 1, minus 4, 3. And there you go. There's your cross product. The reason why I like this so much is because I don't have to, do a bunch of collecting terms. That I've got I times a value, j times a value, k times a value. So I think it makes the factoring a little easier. So we have I times, and now you just have to do your 2 by 2 determinant. So 1 times 1 minus 1 times 3 minus j, and then it's 2 times 1 minus 1 times -4 plus k, 2 times 3 minus 1 times -4. And so what do we get? -2i, and then we got 2 plus 4 is 6, but it's minus on the outside, so minus 6j plus 10k. We'll say WER. So you can see we got the same answer. I kind of like this approach because, again, I think it makes the factoring a little easier. That's just my perspective. It doesn't really matter. You can do whichever one you want. The one thing I would emphasize, though, is I really would get comfortable with at least one of these methods, because we're going to be doing a lot of cross products in this class, especially when we're looking at moments for exam 2. The one thing I do want to close the lecture with is that this is also a task that can be achieved with your Casio. Okay, so I'm going to pull this up. I have a Casio emulator here. I should have pulled this up at some point in class between the time I recorded this video and now, so you should have seen this before. So what we're going to do is we're going to do this cross product that we just did using this calculator. And so I want to show you how that works. So first off, let me go to the slideshow here. Let me see. Actually, let me see if I can move this window up. I want to move this window up just a tad so that we can see the vectors. There we go. So we can see those two vectors right below the window. Okay, so here's your calculator, and what we're going to do is we're going to go to mode, the mode button, and we should have used mode 5 already to do equation solvers. We're going to use mode 8 for vectors. Okay, and so the first thing it'll ask you is what vector do you want to define. The calculator will let you define 3 vectors. So we're going to use vector A and vector B. So let's do vector 1, and it's asking you, is it a 3-unit vector, like a 3D vector, or is it a 2D vector? We'll say it's a 3D vector, so we'll do option 1. And so here we go. So we have vector A, so 2, 1, and so I'm entering 1 and just pressing equals, 1 equals. And so that's vector 1, 2i plus j plus k. And so we can just, once we've got that, we can just hit the AC button and clear it. And you can tell that you've done everything correctly, because if you look at your display, you should see VCT popping up. That should indicate that that vector's been defined and that you're in vector mode. So now we go back to mode 8. Now we'll do vector B. And again, it's a 3D vector. And now we'll define the next vector, -4, and we'll use the negative value, not the minus sign above recall. So equals 3 equals 1 equals. Boom, vector B is defined. And in order to do the cross product, if you look here at your number pad, so over the number 5, do you see how there's a shift button? Or the shift function for vector. So we hit shift button and we hit vector, and so now you can start to see some of the functions here. So we do vector A. Now we're going to do vector A, but before I pull this up, if you notice, see how option 7 is the dot product, and see how there isn't an example for the cross product. So what you do is vector 3, or number 3 for vector A, and you just do the times button for cross product. So the default multiplication is the cross product. You have to tell it to do the dot product. Shift vector A times vector B is the cross product, and there you go. So -2, -6, 10. So you can do this with your calculator as well. It's really not that difficult. It's a little bit more cumbersome, I think, than probably it is worth, but it is a good check. The one thing I would definitely not do on your calculator is dot products. Dot products are way simpler. We devoted an entire lecture today to cross products. We will devote about 5 minutes to dot products because they're very simple. The only other thing I have that's worth mentioning, and I did sort of gloss over it, but I do want to go back to the notes to show this, is that if you go to the slideshow and you go up a few slides to this right here, one of the things that we didn't really emphasize in this video, but we might look at later, is remember that the cross product will help you determine the area, or the magnitude of the cross product is defined as the area formed by the parallelogram between these two vectors. So if I know the magnitude of vector A and I know the magnitude of vector B, and I have the cross product and I can determine its magnitude, well, the area of a parallelogram is defined as AB times the sine of that angle. So one of the other values of the cross product is if you have 2 arbitrary vectors pointing in 3 dimensions, the cross product can help you determine what's the angle between those vectors. That's kind of tough in 3D, but while the cross product may seem a little cumbersome at first, determining those areas, determining that angle, it's a really efficient way of doing this. What I'm going to do is I'm going to assign a homework where I give you a couple vectors to compute cross products for. If you can follow what we did near the tail end of the lecture with the 2 examples, I think you're going to find cross products are very, very straightforward. That is all I have for this lecture. I think we are right at 50 minutes, so I think the timing worked out beautifully. And that's all I have. I will see you all next week.